Hi, everyone. Welcome to our colloquium today. It's a pleasure to have Karl Pertsch join us. He's currently a postdoc at Berkeley and Stanford, and he also spent some time at Physical Intelligence. His work focuses on building generalist robot policies that can solve a variety of manipulation tasks in the real world. Before this, he was at USC, advised by Joseph Lim, and he's won a bunch of Best Paper awards. On a personal note, I'm not one for shock and awe, but Karl's policies worked out of the box here at UW with no training, which I think hopefully he can tell us more about today. But he's done some of the most exciting work in this space. And so it's a pleasure to have him here.
Thank you. All right. Excited to be here in this big room with lots of space. And excited to tell you guys a little bit about the work that I've been doing over the last 2 years on trying to unlock scalable robot learning in the real world. And so if we look at many domains of machine learning, we have seen a lot of progress over the last 2 years on things as diverse as language understanding, coding, maybe most recently reasoning. And this progress hasn't just been limited to the kind of benchmarks that I show here. We have actually seen this in our everyday lives, right? Where now these models help us write better emails, write better code, maybe understand or even generate realistic-looking images. But there is a large part of our everyday life that these models haven't been able to really have an impact on, and that is the physical world. And there are many things in the physical world that we would maybe want some sort of assistance with, from household chores to taking care of others and maybe mundane physical labor tasks. But because fundamentally these kind of generalist models that we're developing in machine learning lack the ability to interact with the real world, they aren't of particular help in these domains. So where are we in terms of actually trying to help us with physical tasks? Well, if you look at most of the robots that are actually being deployed today, they're typically deployed in what you may call structured environments, where a priori we can kind of tell what kind of objects they need to interact with and what kind of motions they need to perform. And so the way that we solve these problems typically is that we have some expert ahead of time pre-program some behavior routine that the robot then executes over and over. Now, clearly this is not a very viable solution for open world manipulation, where we can't make those same kind of assumptions. And so over the last few years, we have seen a lot of progress on an alternative paradigm for teaching robots how to do certain behaviors, and that is the paradigm of robot learning, where instead of pre-programming those behaviors, we essentially teach robots how to do tasks from data. For example, by having humans teleoperate robots, provide a few example demonstrations, and then we have developed methods that can actually learn quite dexterous and complicated manipulation tasks, like the one you see in these videos. And these methods are now robust enough that essentially hobbyists on Twitter within a few hours can get their robots to do meaningful things. Now, the caveat with all of these methods is that they're fundamentally training specialist models on individual tasks and rather small data sets. And because they're machine learning models trained on small data sets, what we find is that they're often brittle. Essentially, small changes to the lighting or an accidental bump on the camera can drastically reduce the performance that these policies actually achieve. And then on the flip side, if you want these policies to be robust and be robust to some of these kind of changes, you need to collect lots and lots of data, and you need to repeat that process for every new task that you want to teach the robot. So where we are today is that we have these powerful generalist models that we train with modern machine learning pipelines on huge data sets. And they do generalize broadly, but they fundamentally lack the ability to interact with the real world. And on the other hand, we have these somewhat specialized robot control policies that are dexterous and can perform complicated tasks, but lack the ability to actually generalize and work on many of the kind of in-the-wild tasks that we may want to deploy them in. And so in today's talk, I want to discuss my research where I try to take these two components and essentially combine them to build something like the modern scalable machine learning pipeline for robotics. And the core idea is that I create these diverse robot learning data sets and then use high-capacity models to train on these data sets. And what comes out of it is what I would call a generalist robot policy that, much like foundation models in other domains, may be able to solve a diverse set of real-world tasks out of the box, and because it has been exposed to quite a bit of robot experience ahead of time, may be able to fine-tune much more efficiently to new tasks and new embodiments. Now, you may say, that's not a particularly hard idea. You just throw a lot of data at a big model and you hope that it will work. But to understand why this may be challenging for robotics, we need to look at what are the typical key ingredients that you need for actually building such generalist models. And I want to say that there's typically 3 core ingredients that matter when you want to build a modern generalist machine learning model. on the one hand, you need to have a large and diverse data set, and typically we go to the internet, we scrape, and then we maybe curate. Secondly, you need a large and high-capacity model that you can actually train on this data set. And then finally, you need to have a set of evaluations that tell you whether that model is any good for the kind of tasks you care about. And so while we have developed these pipelines in other domains of machine learning, actually doing this for robotics turns out to be particularly challenging. Because for starters, we cannot simply scrape robot data from the internet. The kind of model architectures that we have developed for other domains of machine learning, like vision or language, aren't out of the box particularly well suited for dexterous robot control. And finally, it turns out that benchmarking robots and evaluating them at scale is particularly tedious and not easily reproducible because you actually need to deal with real-world hardware. And so because of those challenges, while there is a lot of talk about foundation models in robotics, actually implementing that modern machine learning pipeline is quite a challenge. And in today's talk, I want to cover some of the work that I've done over the last 2 years to try and overcome those challenges, which have allowed us to go from the kind of single task and specialist robot policies that we had before to a new class of generalist policies that are actually a little bit more like how you would interact with an LLM, where you just like download a checkpoint and you prompt it in natural language, and it can do quite a broad set of tasks in a broad set of environments, as Abhishek mentioned earlier. And so in today's talk, I want to capture some of the algorithmic improvements that have led us to this stage, and I also want to capture some of the research infrastructure that I have built over the years to enable research on these problems, namely some of the largest open source robot data sets and some of the most widely used generalist policies that we have in the community today. So without further ado, the outline for today's talk is basically I want to capture those 3 key elements for the scalable machine learning pipeline in robotics, which are large robot data sets, generalist model architectures, and then some work on scalable evaluations for robotics. All right, let's start by talking about data sets. And when I started working on this problem of training scalable robot models, there were already a few robot learning data sets out there that people had developed for the purpose of being larger scale. And they were all around that, like maybe 70 to 80,000 episode scale. But what was striking is that many of these data sets weren't actually particularly diverse. They were often collected in maybe a handful of scenes, doing a handful of different tasks, but not of the kind of diversity that we would need to actually have policies generalized to the kind of new environments that we care about. And so the core problem that we were trying to address is how can we get more diverse robot data that actually supports generalization into a broader set of environments. And the problem is that it's really hard for any single entity to actually collect diverse robot data, because you can imagine in order to collect diversity, you need to have potentially many different robots and you need to deploy them into many different environments for people to collect data on them. And so the core idea that I had to try and overcome this problem is to leverage the power of the community. So while it's very hard for any individual to actually collect diverse robot data, it's much more feasible as a community to work together to try to address this fundamental problem that we were facing. And so over the last 2 years, I have led multiple larger scale efforts across the robotics community on trying to both collect and then also pool robot data. These were collaborations including more than 30 institutions and 200 robotics researchers from around the world. And in today's talk, I want to focus specifically on 2 of those collaborations called Droid, which was a project on data collection, and then the open cross embodiment for dataset pooling. So in Droid, specifically, the problem that we were trying to address is to get data that is a little bit more in the wild, essentially closer to the kind of data, to the kind of environments that we would want to deploy these robots in. And so specifically, we tried to collect data in actual people's homes, in bathrooms, kitchens, living rooms, and so on, to then support generalizable policies that could actually be deployed in those environments. And as I had mentioned, while this is very hard for any individual to do, we essentially organized this larger collaboration with more than 50 grad students that reproduced this robot setup for data collection. It's a single-arm Franca robot setup with multiple cameras. And over the course of roughly 2 years, we collected this new data set called Droid with roughly 70,000 episodes. And here, when I talk about data, I specifically mean essentially image observations, proprioceptive state of the robot, and then some sort of action representation. And it was teleoperated by humans to perform various tasks in their actual homes. And while the size is comparable to existing data sets, you can see that the diversity is significantly larger. If you look at some of those examples here, to put some numbers on it, we tried to collect data in more than 560 different scenes and maybe 80 different tasks. But there's lots of auxiliary diversity that we see in terms of viewpoints and lighting conditions and so on, which will help us train more generalizable policies. The other thing that this project taught us is how hard it actually is to scale up robot learning data, because we needed to collect it over the course of 2 years, and we ended up with maybe around 70,000 episodes, which is still a far shot from the kind of large-scale data sets we have in other domains of machine learning. And so what we asked ourselves is whether there's a way that we can actually try to scale up robot data faster than what we could do by collecting it ourselves. And the core idea that we had is that there is actually a lot more robot data already out there. It's just typically hard to get to. And the reason is that a lot of us, robot learning researchers, actually work on various types of robotic setups. I'm showing a few examples that we have at Berkeley here. And on each of these setups, we typically collect data to support our research. We just don't usually share it with each other or try to reuse it. And that's because each individual data set may not be particularly useful for somebody with a different robot. But the idea that we had is that if we could take all of those data sets and pool them together into an easy-to-use kind of coherent resource for the community, then maybe as a whole they would be much more useful to support kind of scalable robot learning research. And so this is the core idea behind the Open Cross-Embodiment project, which was a large collaboration that I co-led with a colleague from Google, where we essentially, over the course of just a few months, aggregated existing data sets in the robotics community to build this Open Cross-Embodiment data set, which at the end had more than 1 million real robot episodes, now spanning 22 different robot embodiments. And so if you look at the data, you can see that it is more diverse, and it now not only spans different scenes and skills, but also different robot embodiments on which we aggregated these data sources. And so after we released this data set in a way that many people could use it, I think the main impact that it had is really that it allowed the community to do research on a new type of problem, where instead of trying to collect bespoke task-specific data sets for each project from scratch, we could shift to a type of research where we reuse general purpose data sets that were collected once and then used for many projects in a row. And in that mode of operation, it's essentially much more feasible to actually build large-scale robot learning projects because nobody would recollect ImageNet every time they want to start a new project. So reusing is really key. And we have seen a lot of people build on top of our work here. They have used the Open Cross-Embodiment dataset for various types of robotics research, from video prediction models to kind of general camera calibration or policy training research. And we have also seen people follow up on our work and actually build their own data sharing efforts, be it for this kind of tool-based manipulation interface that was developed at Stanford, or also the first companies that are now sharing meaningfully sized robotics data sets with the community. So to summarize, basically what we discussed is that the introduction of these larger scale robot learning data sets through community-wide collaborations has allowed us to essentially go from single task and domain specific data sets to now much more general purpose, kind of reusable robotics data sets. And while a lot of this work was around building community and building infrastructure, I think it was really necessary to do this work to then support the follow-up research questions on how to actually deal and learn from this type of data. Because when we introduced these new data sets, there were new challenges that we needed to solve. Now you need to train policies on hundreds of millions of robot samples and on data from many different platforms that have potentially different sensors and different actuation interfaces. And so in the remainder of today's talk, I want to capture some of the work that we have done on actually leveraging those data sets to build the kind of generalist policies that I'm interested in. So let's talk about how we can actually train models on these data sets. And before I want to talk about the exact models we're training, I want to define the problem a little bit. So in most of today's talk, I will use a technique that's called imitation learning, where essentially we assume that the data set we're given is of high quality, consists of high quality demonstrations, which is the case for most of the Open Cross-Embodiment data set. And so then the way that we will actually train policies on this data is that we will train them essentially with supervised learning, try to maximize the likelihood of actions in the data conditioned on some sort of observation and some task identifier. And to make this very concrete in robotics, the observation may be something like an RGB camera stream and some proprioceptive information. And then the task identifier in most of the work that I do is a natural language instruction that essentially tells the robot in a string what it's supposed to do. And then the action is very robot dependent. It depends on which kind of robot platform you're working with. But for this kind of simple end effector type, single end effector robot, it could be something like a 7-dimensional end effector displacement action, where it's a free translation, free rotation, and one gripper dimension that you're controlling. So that's the problem we're trying to solve. The challenge, as I mentioned, is that we're trying to solve it on this large cross-embodiment data set where we have potentially hundreds of millions of samples, and they're heterogeneous with various types of inputs and outputs. And so the kind of architectures we need to develop need to be scalable to support that size, but also flexible to actually enable us to handle these types of various inputs and outputs. And so over the last 2 years, I have worked on this problem quite some time, both in my PhD and then more recently in my postdoc, and I want to take you guys through a little bit of a tour of how my thinking has developed. So during my PhD, I started working on what I called skill-based learning at the time, where essentially we learned from data sets, skill embedding spaces, latent spaces that represented kind of atomic skills that we then used to bootstrap downstream learning on new tasks. And while this did help speed up downstream learning, it was still quite rigid, kind of assumed fixed inputs and outputs for the low-level skills. And so when I switched to being a postdoc, I started working on more modular and flexible policy architectures. We built this model called Octo, which was inspired by the tentacles of an octopus, and it was a bit more flexible in that it supported different kinds of encoders and action decoding heads that allowed you to train it with different types of input modalities, goal or task identifiers, and output actions. And while this project or this model was actually a bit more flexible, it was also a bit not very elegant, because now you had to keep around all of these different types of encoders and decoding heads, and you had to switch them out depending on what kind of robot you wanted to use. So right around the time that we actually finished building these larger scale data sets, the robotics community as a whole kind of discovered a new hammer. And that hammer was the large autoregressive transformer, or more specifically, the vision language model. And what made many people excited about vision language models is that they were inherently able to process various types of multiple high-dimensional and low-dimensional inputs, as well as produce flexible length outputs. And of course, they were scalable because they were designed for being trained on billions of images from the internet. And so me and a lot of other people got quite excited about trying to use these models for robot control. And at the time, I was a student researcher at Google, and some other folks at Google started this project called RT2, where they tried to take a vision language model and fine-tune it for robot control by essentially embedding robot actions into some tokenized representation that these models can work with, and then fine-tuning the VLM to output those robot action tokens so that they could predict the kind of control outputs that we need for robot control. And to repeat, basically the key features of these models were that they supported flexible inputs and outputs. They were able to be trained on large-scale data sets, and if you initialized them from VLM weights, they supported some sort of transfer from the kind of internet-scale pre-training in terms of the kind of objects, for example, that they were exposed to ahead of the robot data. And so this project happened at Google. I was only minorly involved, but the whole outcome of the project was somewhat specific to Google. We had trained it on Google robot data and with Google proprietary VLM models, so it wasn't particularly useful anywhere else. And so when I started my postdoc, I wanted to work on my own version of a VLA, essentially a state-of-the-art open source model to support research in this direction. And so we started this project called OpenVLA with some collaborators at Stanford, where we tried to kind of dissect the design space of these models and understand how to build a good open source vision language action model. And so what we figured out pretty quickly is that there is essentially two questions you need to answer when designing a VLA model. On the one hand, what backbone do you want to use for your model? And then how do you want to represent actions to actually train the model for robot control? And in OpenVLA, we used at the time the state-of-the-art LLM model, which was Llama 2 in ancient times. And we figured out that it's actually quite beneficial to use a two-stream vision encoder that combines the semantic clip features that are often used in VLMs with spatial kind of Dino V2 style features that capture more about the exact positions of objects. And so we found that this helps policies perform better downstream. And for the action representation, we stuck to the same representation that was used in the original RT2 work from Google, which is a simple binning tokenization approach, where you take your continuous actions, you take the range of action values in your data set for each action dimension and divide it into 256, or whatever hyperparameter you want to choose, uniform bins. And then the way you assign an action token to each bin is by essentially checking which of those bins your continuous value falls into, and then assigning the discrete integer value of that bin as your action token. And so this is essentially a fancy way of saying you bin tokenize your actions to go from continuous to discrete action tokens. All right, so once we had tokenized our actions, we could train the OpenVLA model on the cross-embodiment dataset that I had mentioned earlier using this open source model. And then the way we evaluated it is by testing it in two regimes. On the one hand, out of the box, essentially on robot platforms that had been seen in the training data, as well as in a fine-tuning setting, where we took the original OpenVLA model and fine-tuned it with some in-domain data on a new robot platform or a new task that the robot was performing. And we compared some of the kind of from-scratch robot-only trained models that I had developed earlier, like the Octo model, to the OpenVLA model, which was significantly larger in scale and initialized from VLM weights. And we compared them on these two scenarios, and we found that there was a significant difference in performance from using our VLM initialized model. And this was a somewhat surprising result to me because we actually worked quite hard on building this Octo baseline, but it was clearly outperformed by this VLM model. We also compared to an kind of internal to Google version, the RT2 model now trained on the cross-embodiment dataset, and found that our open source model was actually able to outperform this policy, in part due to the kind of improved encoder architecture that we had developed for OpenVLA. So this was a nice result. We released this model. People started actually using VLA models in the community a lot more after that. But for us, this wasn't really the end of the story. It was really just the first step to allow us to do research on these problems. What we were really interested in is to try and train these models to do dexterous control tasks that involve complicated and fine-grained motions, like in this laundry folding task here. And so we had developed OpenVLA. I was really excited about training it on these kind of tasks. But what I found after I trained the model is that it doesn't actually work very well. So you can see I sped up this video 40 times. It's really slow in real time. And you can see that even in that case, it doesn't quite do a nice fold at the end. So the OpenVLA model applied to this problem turned out to be essentially slow and imprecise. So what this showed us is that the naive VLM recipe that we had developed kind of doesn't provide sufficient dexterous control when you actually try to apply it to these more complicated robotics tasks. And the question that we were trying to answer is how to represent actions in a way that they actually support these kind of more complex robotic control problems. And at the time, we tried to approach this from two different angles. On the one hand, with colleagues at Physical Intelligence, we built this model called Pi0, where we repeated the idea of, or kind of reused the idea that we had originally developed with the Octo model, where we introduced specialized action decoding heads. So in this case, we use a VLM backbone, but then introduced this diffusion action decoding head, which turned out to work pretty well on kind of more dexterous control tasks. But it wasn't a very satisfying solution to me because we hadn't actually understood why the original OpenVLA model didn't work. And so at the time, I went back and I tried to really understand why does the action representation that we used in OpenVLA not provide sufficient representation for dexterous robot control. And to answer this question, we need to dive a little bit deeper into how these models are actually trained, but I hope that you will bear with me as we go through that exercise. So the way that we train VLA models is typically that we ask them not only to predict a single action, but an action chunk, which can be something like a second of future action trajectories. And if you do this on a low-frequency control problem, like those tabletop manipulation tasks, they're maybe operating at something like 3 hertz. And so if you apply that original binning tokenization that I talked about earlier, you'll end up with an action matrix with 3 columns as entries. But now what happens as you increase the control frequency of your problem is that you essentially increase the columns in your matrix. And so when you go to very high frequency control problems, like those dexterous laundry folding tasks, typically we do those at something like 50 hertz, you end up with a lot of columns in your action matrix. And what we find is that in these columns, there ends up being a lot of repetition. And this is maybe not a very surprising observation, because if you have a continuous time signal, you sample it at higher frequency, essentially you will increase correlation between your samples. So why is that a problem? Well, if we actually look at how we train these models, we typically take this action matrix, we flatten it, and then we train the autoregressive transformer with a standard next token prediction objective. It's the same objective we use for training language models or vision language models, where conditioned on all the previous tokens, you make the transformer predict the very next token in the sequence. However, the problem is now, if those tokens are highly correlated, then basically the training signal you're using here, which is the marginal information of each token conditioned on all previous tokens, decreases, right? Because those tokens are correlated to each other. And as a result, the training slows down and the models are essentially incentivized to copy over tokens because all of those prior tokens look very similar to the future tokens you're trying to predict. So to summarize, when we take the naive OpenVLA model and we apply it to these dexterous control tasks, the problem we are facing is that we have a lot of tokens with low information density in each token, and as a result, training slows down and basically doesn't converge effectively.
This also happened for the Pi0 style model?
So in Pi0, it's a non-autoregressive architecture, right? Because we do diffusion decoding, and so in that case, you don't have that problem. It's basically a problem that specifically shows up when you want to do the kind of standard autoregressive style of model training. And so we will have a comparison between Pi0 and this style of action prediction later. It's a good question. Okay, so what can we do? Well, the simple idea that I had is that if our problem is that we have a long sequence of low information tokens, then maybe one way we can address it is by trying to apply compression. Because compression essentially allows you to increase the information per token while reducing the number of tokens. And as a result, the hope is that we can actually train effectively even on high-frequency data because we retain high information in each action token. Then the question is, how can we actually compress actions effectively? And the solution that we came up with actually relies on a very classic signal compression technique based on the discrete cosine transform, or DCT, which is a technique that you probably use quite a lot in your everyday life because it's the same basic algorithm that's at the core of JPEG encoding or MP4 video encoding. And the way that DCT-based compression works is that DCT takes a continuous time input signal and represents it as a weighted sum of cosine signals of various frequencies. And the key property that makes DCT so nice for compression is that it typically can represent continuous time input signals as a sum of just a few high-weighted coefficients or high-weighted cosine signals, and then most of the other frequencies in your mixture will turn out to be weighted around 0. And so during compression, you can just get rid of those low-weight coefficients. So to summarize how we take this DCT approach and actually put it into an action tokenization algorithm is that we start with our continuous time input. We convert it into its DCT coefficients. And then if you do that for each action dimension separately, you end up with a matrix like this. And then if you round it or quantize it, you can see that most of the coefficients end up being 0. This is the property that I mentioned. And so then to compress, we can flatten that matrix and compress it with whatever lossless compression algorithm you like. In our case, we use byte pair encoding, which is a commonly used one. And you end up with this rather short sequence of high information density tokens that we can then use to train our VLA model. So to summarize, to use our tokenizer, which we called FAST, you essentially take your continuous time signal, you compress it through the DCT-based action compression approach, and then you end up with this short sequence of high information action tokens that you can then use to train your typical autoregressive VLA model without any change to its architecture or training algorithm. Okay, does this actually work? We tested this on a bunch of different data sets from rather low frequency control, these simple kind of tabletop manipulations, to more complex shirt folding style problems. And we compared across those data sets the kind of naive tokenization that we had used in OpenVLA to our maybe more advanced compression-based fast tokenizer. And you can see that across all the data sets, we do see compression that we can achieve with the DCT tokenizer, and particularly so for the kind of high-frequency control tasks, where the original OpenVLA tokenization gives you a lot of action tokens with low information density, and we achieve a more than 10-fold compression in the action token signal. Does it actually help policy learning? To test this, we trained a bunch of VLA policies, all using the same backbone architecture, just changing out the action representation, essentially the tokenization approach. And we find that particularly on these kind of higher frequency control problems, like the t-shirt folding task, there's a clear difference between the OpenVLA style of tokenizing actions, which essentially doesn't work for training policies on these problems, as we had established, and the fast tokenizer, which allows these policies to actually now train effectively on these kind of tasks. We also did compare to another baseline based on vector quantization, which is a quite typical approach for training or for tokenizing high-dimensional image inputs, for example, in neural network training. But what we found, the way that this works is that you train a neural network to essentially compress and decompress your input domain, and then you train your actual model on the latent representation of this network, and then just decode back into actions using the decoder. And we found this to be quite a bit harder to train, because you now need to actually train and tune neural networks to do the compression for you. And even after that, we found the representation to not be particularly effective for policy training. So our fast tokenizer essentially allowed a better trade-off of complexity and downstream policy performance. So these were encouraging results. We then tried to take this model and actually scale it to a larger training data set. And we trained this model we called Pi0 Fast, which was trained on the open cross embodiment data set that I had mentioned earlier in the talk, as well as some dexterous manipulation data that we collected after the fact. And when we trained this model, we found out that it actually is now able to solve these kind of very complex and long horizon manipulation tasks, like this laundry folding task, which I think the video is a little bit too long for me to play in full, but I hope you can believe me that it can actually fold 5 laundry pieces in a row in this fairly complicated manipulation problem. But not only were the policies dexterous, I think my actually favorite result from this paper is the generalization aspect. So here's a model that I trained with the fast tokenizer on the droid dataset, like fine-tuned it on the droid dataset that I had mentioned earlier. And the way that this model was evaluated is that I sent the checkpoint to a few of my collaborators in the US, in Canada, also here at UW. Thanks, Abhishek. And the way that they use this model is a lot more like an LLM, where essentially you can download a checkpoint, you can put it on your robot. Admittedly, not any kind of robot. It needs to be a droid robot in this case. But then you can simply prompt it in natural language to do various types of tabletop manipulation tasks, and it will typically do a reasonable attempt. And this may be kind of familiar to people working in language modeling, where it's now quite usual that you download a model and you prompt it and it does something reasonable. But in robotics, this didn't used to be the case. Learned robot policies, typically you would need to fine-tune them with some in-domain data that you had collected in your particular lab, with your particular camera angles and so on. But this was kind of the first time that we saw one of those generalist policies actually being able to be deployed zero-shot, where you just download it, prompt it, and it kind of works. And this was kind of a surprising result, I think, to us, and really paves the way towards more general and reproducible type of robot policies. All right, the final result I want to talk about in this paper is that we also compared our Pi0 Fast model to the original Pi0 model. So to remind you, that's the model where we had introduced the specialized action decoding mechanism. And what we found is that when you train them on fairly large-scale data sets, there was actually a significant speed increase in training iteration speed, training convergence speed between our Pi0 Fast model and the original Pi0 model. So our simpler architecture essentially ended up training significantly faster. And so these training runs on this curve can take a few weeks to complete, so being able to do them 5 times faster actually significantly accelerates the kind of research iteration that you can do on these models. And so by today, this fast-based Pi0 model is actually the base model that we now base all of our research on going forward, just because it's easier to train. All right, so to summarize, basically the problem that I was trying to solve is to design scalable yet flexible robot policy architectures to train on these larger scale data sets. And then the solution that I came up with is to train vision language action models, but train them using the right type of tokenization representation that actually allows us to do both dexterous control and generalize to unseen environments out of the box. And we have seen quite a bit of follow-up research that builds on top of these models that we developed. The OpenVLA model is now downloaded nearly half or a bit more than 500,000 times, which is quite a bit more than existing other robot models. And we have seen a lot of people in academia follow up on this research, try to improve the VLA recipe, make them more efficient, make them generalize better. And we've also seen industry labs starting to pick up these models, try to run them on their problems, and try to make them run efficiently on their platforms. All right, so we have talked about data sets, we have talked about models. I want to use a few minutes in today's talk to also talk about evaluations. I think this is a really important problem that often gets neglected a little bit in robotics research and how we talk about these papers, but I think it's a really impactful one to work on if we want to move the robotics community forward. So what we have seen in many domains of machine learning is the importance of scalable and reproducible evaluations. We have seen this from, of course, the original ImageNet competition, but also more recently on the kind of larger scale language model benchmarks where people have used evaluations like MMLU to guide their research progress. So what we have seen is that scalable and reproducible evaluations really help us accelerate and guide the kind of research iterations that we're doing, and also make research a lot more cumulative, where essentially I can now much more quickly tell whether a problem or a solution works or not, based on the way it performs in a common benchmark. Now, in robotics, the situation has been a little bit different, where actually doing evaluations on real robot hardware is somewhat tedious and slow, because you actually need to run real robot systems in real robot environments. And it's also very hard to reproduce. Right? You can imagine that reproducing an initial state in a real-world environment is challenging. And even your robot itself may, over time, drift in its characteristic as it's getting worn out through its lifetime. And while these problems are kind of annoying when you work on single-task policies, they get really challenging to deal with when you want to develop generalist policies, where now you need to do evaluations across many tasks, many scenes, and potentially even many embodiments. And so one thing that I've learned over the kind of many generalist policy research projects that I've been a part of is that evaluation is really one of the key bottlenecks if we want to develop these methods forward. Because finding ways to scalably and reproducibly evaluate these policies is really key to allow us to understand whether the things that we're introducing, the ideas we're working with, actually make these models any better. And so I want to cover one work in today's talk that we have done in that direction, trying to address the scalable evaluation problem for robotics. And the first thing that we did in this work is to actually try and formalize this problem of developing scalable evaluations. And the way that we formalized it is assuming a given set of n policies that we want to evaluate and a set of ground truth human evaluation scores. For these policies, what we want to build is a scalable evaluation pipeline that can give us estimates for those scores, and hopefully an easier and more scalable way. And then we developed some metrics to actually measure whether a given scalable evaluation approach works or doesn't. And those metrics essentially try to compare those ground truth human-run evaluation scores to the scalable evaluation approach that we develop. And on the one hand, we can look at their correlation, which I guess is a very intuitive metric to test whether they have a clear relationship to each other. But correlation by itself is maybe not enough, because in some situations we don't actually care about exact correlation. What we care about is ranking, essentially telling us that we're making improvements if we look at the ranking in the scalable evaluation approach. In those cases, maybe the correlation itself may not be particularly high, but we introduced a second metric based on a ranking kind of approach, where we try to quantify the rank violation that a scalable evaluation metric introduces, where rank violation is essentially the difference in real-world performance between policies that are misranked in our scalable evaluation approach. And we essentially average over the worst case of such rank violation across all the policies in your set. All right, with these metrics in place, we try to then develop a scalable evaluation approach. And the key idea that we had is that instead of trying to do evaluation in the real world, where it's tedious and kind of slow, we wanted to develop simulated evaluation platforms that are close enough to the real world that policies trained on real robot data would actually work when deployed in those simulations, and would give us indicative success rates of those policies if we had run them in the real world. And the key benefits of doing things in simulation is that it's, well, scalable, it's cheap, it's also reproducible, right? Because you can perfectly control the initial state of your simulator every time you rerun an evaluation. And then the key question is, of course, how do we build simulation environments that are sufficiently realistic to afford this kind of simulated evaluation? And the first step that we tried is a simple kind of domain randomization approach, where essentially we manually created simulated environments that were close enough in their geometry to the original real-world environment. And then we randomized over some parameters of this environment, from lighting to backgrounds to textures. And we tested 4 existing generalist policies that I and others had worked on in 8 different environments that we had previously used for evaluating those policies in the real world. And then we compared to maybe what is the most standard way of evaluating policies in machine learning, which is to look at their validation loss. And we found that our simulated evaluation was actually much better able to reflect their real-world performance than a MSE score, which turns out to not particularly well correlate with real robot performance. And we could have stopped at this point, but we want to really understand like which aspects of the problem allow us to close the gap between our simulated platform and the real world that we wanted to approximate. And we had two different hypotheses that we tried to evaluate, be it the realistic visuals that would help us close this gap or more accurate physics. And to test these, we developed realistically looking simulated environments through a fairly manual process of trying to copy over pixels and then tune pixels for the background from the real environment and tune the lighting on the foreground simulated textures. And then for the physics problem, we tried to randomize over the physics parameters of the simulation, both in terms of the object mass, various type of frictions, and we also compared different physics simulators to try and understand whether they impact the reliability of our simulated evaluation. And so again, we compared on this set of policies, and what we found is that the realistic visuals made a big difference, where essentially policies are seemingly very sensitive to the visual realism of those environments. And so we could see a clear improvement in the reliability of our simulated evaluation by improving the visual realism. But then on the other hand, we didn't find the physics part to be particularly important for the kind of task that we evaluated here, where we didn't see a clear difference in the evaluation performance when we varied different physical parameters or changed the simulator. So our kind of core conclusions from this project were that visual realism is really key for getting good simulated evaluation environments, whereas for the kind of rather simple style pick-and-place static manipulation tasks we dealt with in this particular work, the physics weren't really the key aspect for good simulated evaluation scores. We have seen people use these environments for their own papers, try to use them for policy evaluation, and we have also seen people then build more fine-grained evaluation environments on top of these simulated evaluations to tease apart in more detail how these VLAs work. I also want to fully acknowledge that we haven't solved the problem in any way. I think we have made some progress, but there's still many limitations that remain, both in the visual realism of these environments and their creation, which currently is a quite tedious process of manually engineering sim environments. And there's many tasks that are flat out hard to simulate, so we can't use simulated evaluation to solve them. And so we are doing some ongoing work in both of these directions. We have some collaboration actually with Abhishek on trying to build more realistic looking simulated environments using neural rendering techniques. These are also easier to create. And we have some ongoing work on automated real-world evaluations, where we try to focus on tasks that are hard to simulate, like this cloth interaction task. So to summarize what I talked about today, I hope that I could give you guys a bit of an overview of the kind of key ingredients of scalable machine learning that I have worked for in robotics, both from the larger scale data sets, some of the models that I have developed that allowed us to do dexterous tasks and generalize out of the box to new environments, and some of the early work we have done on trying to build more scalable evaluation tools for robotics. I want to use a few minutes in the end of today's talk to talk a little bit about future work and what we can do building on top of these base ingredients. And I started the talk by talking about real-world tasks that I would like to assist people with. And I think we're still a bit of a far shot away from these tasks and from building kind of a general purpose tool that we can use to help us solve physical tasks. I do believe that the kind of core ingredients that we have put into place are really key to try and make progress on it. And I think if we solve this problem, it will have a big impact far beyond any particular domain, a little bit like how the computer helped us solve and unlock many of the digital tasks. I think a general purpose robotics model will help us unlock many real world and physical use cases that we can deploy robots in. But as I said, I don't think we are anywhere near solving this problem, and I think there's quite a few key directions that we still need to improve on for being able to actually deploy policies into the real world. And I want to go a little bit into detail on these. I think one key limitation that we see in these policies is their ability to generalize to a broad set of new objects. And this is one of the benefits. If you give your policy to a bunch of independent roboticists, they will very quickly figure out all the different limitations that your policy has. So here you can see some of the independent evaluations of the Pi0 model, where people put some somewhat unfamiliar objects in front of the robot, like this toilet seat. And it doesn't quite understand how to actually handle this situation. So while the generalization abilities of these policies is significantly broader than learned policies before it, there are still many ways in which it's limited. And I think there's a lot of potential in trying to unify the kind of embodied foundation models that I work on and the kind of non-embodied foundation models we find in other domains of machine learning. And there's a lot of potential for synergies, where essentially we can learn common sense and how to interact with unfamiliar objects from internet data, as well as teach internet data foundation models about the physical world and how to interact with it from robot data. And we have done initial work here trying to bridge those two domains. We have done work on teaching robot policies how to reason through problems before acting, which significantly improves their generalization ability. But I think there's lots more work to be done at this intersection of these two domains. I think a second big focus that I want to put on in the next few years is looking into dexterity. If you look at a lot of the human examples that I've shown in today's talk, a lot of them involve the kind of effortless, dexterous manipulations that humans perform on an everyday basis. But then if you look at the actual policies that I've trained, they're much less dexterous. They're typically pinch, grasp, and effectors. And we can see that this limits us in many of the kind of everyday tasks that we're trying to solve with these policies. And so I think there's a lot of potential in trying to combine some of the scalable robot learning work that I've done with some of my earlier work on skill-based learning, where you can try to learn dexterous skills, for example, from either human video as a kind of scalable data source, or even in simulation, where we have seen a lot of progress on trying to learn dexterous skills. And I think it's really exciting to try to combine that with some sort of real-world data approach that actually allows us to generalize those beyond simulation. Finally, I think that there's a lot of upside to be had in trying to make these policies easier to work with. I think there's a lot of kind of value that can get unlocked if you make it easy for people to essentially use and alter the behavior of technology in general, and particularly of robot policies. And to be very clear, I think the way that we are currently trying to use these policies is not particularly intuitive. So if you wanted to take one of my generalist policies and teach it a new task, you would actually need to strap yourself into one of these teleoperation interfaces, collect a bunch of demonstrations, and then fine-tune your policy and hope that it actually learns the new task. And while this is not particularly intuitive, I think there's lots of potential now in using these models and try to teach them in more natural ways that are easier for humans. So for example, in this project, you can see that Lucy teaches the robot to do her favorite trail mix through natural language feedback only. And because these models are essentially VLMs at heart, it's fairly easy for them to understand natural language inputs or even human visual inputs in how to alter their behavior. So I think there's a lot of potential in trying to explore this intersection of kind of generalist robot policies and the way that people can actually make use of them and teach them new things. And I'm very excited to also collaborate with faculty here at UW who look into these questions. Generally speaking, I think my approach to research combines contributions to systems and infrastructure with algorithmic improvements and their application to the real world. And I would say that my research sits at the intersection of robotics research and general foundation model research, and I'm really excited to collaborate on a broad spectrum of questions from hardware and sensory development all the way to kind of more fundamental improvements to how we design, for example, vision language models to be able to comply with the kind of limitations and constraints that we deal with in robotics. So with that, I want to close. I hope that I could give you guys a bit of an overview of the work that I have done that allowed us to go from kind of the specialist control policies I mentioned in the beginning to a more generalizable class of robot policies. But I hope that I also outlined some of the big challenges that lie ahead in trying to make those models actually general purpose and actually deployable into real-world environments. All right, with that, I want to thank my many collaborators who have allowed me to do this work, and I'm happy to take any questions.
Great work. Really like it. So in most of the work, you've been focusing a lot on the behavior cloning side with the operation data. What are your thoughts on like reinforcement learning in the wild later on? Because if you will perceive like truly new situations and new tasks, then the robot needs to be able to on the spot without, I guess, always requiring a teleoperation person coming.
That's right. So I think for RL to be successful, especially in real-world domains, it is really important to have a good initialization, essentially some sort of prior that tells you at least what is reasonable to explore, right? Because you can imagine if you put an uninitialized policy in an environment and it just like, flings around its arm, it will not likely make much progress. That being said, I think with some of the policies we've been developing, we have a prior like this now. Like you can actually take those policies and you can put them into a new environment, and they generally act reasonably. And I think in that situation that we're in now, it's much more feasible to actually build RL solutions on top. And I do think it is very important to work on these things. I think the reason it's important is twofold. I think once the kind of reliability that we would actually need for real-world application, like the kind of 99% plus success rate you may want, this is not something we get out of the zero-shot models by any means right now. Like they basically get between 50 and maybe 80% success rate at best. So they're far off from the kind of reliability that you would want for actual application. So that's one reason why it's really important to learn on the job, so to say. I think the other reason is that there may be, especially if we think about these more dexterous style of robotics platforms, it may actually just be very hard to teleoperate them effectively, right? And so in that case, it may be a much more efficient way to train them by having them explore their dexterous end effectors by themselves through an RL process than trying to supervise all the way. Yep.
Question about the compression. You used DCT compression, and apologies if you already covered this, but I'm curious how much of that compression space did you explore, and what do you think of the possibilities for that in the future?
Yeah. So we did try a few other compression alternatives. PCA is kind of the other easy alternative. We also tried the neural compression, which was one of the baselines that I mentioned. The general gist of those results is that they all kind of work the same in terms of how much they can compress the input signal. I think there's a certain regularity in robotics action data where actually if you look at the kind of dominant directions that PCA learns, they still look quite sinusoidal. So they essentially recover the same basis, roughly speaking, as the DCT approach. So I think the kind of headroom on how much more can we compress the data isn't too large, and there's also a little bit of a kind of two-side optimization you're trying to do here. Like it's not always better to compress more, right? Like we have seen this in in vision language models, where it's actually not necessarily said that a compression algorithm that gives you less tokens leads to better downstream learning, because potentially the representation that you learn is much more entangled, and then it's harder actually for a policy to understand how to predict over that representation. So my general kind of intuition here is that I feel there isn't too much more to be gained. I'm sure we can come up with other compression algorithms, but what we needed was essentially a way to homogenize and compress information to a level where it's trainable. But now kind of the returns in my mind are rather diminishing, would be my guess. We haven't exhaustively explored. And I think the more important questions will be how to build stuff on top of it. We have kind of figured out the base representation that's reasonable. Yeah. The other benefit of the DCT style representation I want to mention is that it generalizes quite broadly. So we have trained this tokenizer on a bunch of robot data sets, but we can now apply it to new robots. So actually at Pi, we have never retrained this tokenizer ever. So even if we add new robots to our fleet, it basically usually generalizes quite nicely, even to new action spaces. Yeah.
Questions? Maybe just on the topic now. So intuitively, one would say for policies like diffusion models are really nice, right? Continuous and all the one-step outputs. And what are your thoughts now after having developed the fast tokenizers on autoregressive versus diffusion kind of policy outputs?
Yeah. So where we have seen diffusion models succeed mainly is in domains where you need to decode high-dimensional outputs, right, like images or videos. Yeah, in the action domain, I think the dimensionality of the output isn't high enough to require them. I think the autoregressive models are very competitive. Now, I think there are some kind of second-order things that we care about. So training speed is one, I think, where we see a clear benefit from the autoregressive representation, which just converges significantly faster. The other one that is a little bit less obvious is language following. So making policies condition well on language inputs is a really important problem. We often find that policies tend to be rather unconditional, where no matter what you tell them to do, they will do the thing they like, which is not very useful, right? You want policies to listen to you. And so what we find is that in these autoregressive models, the prior to listen to the language input is much stronger. Because in the diffusion models, you can imagine we introduce a new set of weights initialized from scratch. And so my guess is that the learning dynamics basically favor a solution in that case that ignores the language inputs and just tries to match the action outputs roughly based on what the image observations tell you. Whereas in these autoregressive models, we find that they're much easier conditioned on language and pay more attention to the input language. And I don't think that there is something fundamental about the learning problem that's different, right? We're doing the same inputs, the same outputs. It's some kind of optimization-based difference, where essentially the initialization with an autoregressive model that already pays a lot of attention to tokens when predicting future tokens makes this model easier conditionable on language. And so that's why right now this is kind of our base recipe. It's faster and it conditions better on language. Now, whether that will hold in the future, I don't want to, make strong predictions. I think both models seem quite competitive, so we'll see.
I have a question. In terms of safety on deployment around human-centric environments, how do you guys think about that? And how do you
so we haven't addressed the safety question much. Basically, because our models are trained through imitation learning, they're inherently reasonable-ish in most environments, right? Because they're trained from human examples, so they're not likely to explore crazy solutions. I think giving safety guarantees is very hard for these models because they're fundamentally hard to analyze. The way that I think about approaching the safety problem is through statistical safety, essentially trying to evaluate models in many different environments and getting a statistical sense of how likely they are to, not be unsafe. And so some of the work on simulated evaluation, I think, can help with that, where we can evaluate very quickly on a very broad spectrum of tasks, and then probably there would be a secondary phase where you essentially deploy into real-world environments, but with a human supervisor that is trained to handle these situations. I think more formal guarantees for safety is an interesting problem, but it also seems much harder to approach. If you actually do open-world manipulation, there's all types of common sense safety that you need to think about, which seem very hard to formalize. One kind of hopeful signal is that there is some evidence that models can potentially translate safety concepts between different situations at large enough scale. So maybe we don't need to teach them each and every incident that is potentially unsafe, and they can kind of generalize this notion of generally safe to new environments.
We are at time, so unless anyone has any other questions, let's thank God.